we're going to start our look at rational functions by looking at their graphs. So the first thing we want to do is talk about what a rational function is. A rational function is a polynomial over a polynomial. So it will be in the form, it will look something like this, where you have a fraction, where you have a polynomial in the numerator and a polynomial in the denominator. Today, though, what we'll look at for this lesson is we're going to look at a linear binomial over a linear binomial. We're not going to look at, we'll look in the future at adding quadratics or constants or cubics, things like that. But for today, we're just going to look at when we have a linear binomial over a linear binomial. So let's look at the format of this. The format we're going to look at will help us understand why the graph does what it does. It will be a fraction with a constant of some type and then adding a constant on the outside. Now, when looking at this format, this value will tell us what the vertical asymptote will be, and this one will tell us what the horizontal asymptote will be. That's what we're looking for to get insight by looking at this format. We won't always use this format, but that will help us here. So when we look at the vertical asymptotes, this is when the denominator equals 0. Since the denominator is not allowed to be 0, the asymptote, which is a value we don't actually get to, we get close to, we set the denominator equal to 0, we get that value, and then we draw a vertical dotted line for that asymptote. Now, for the horizontal asymptote, this is actually the end behavior of the graph. So that'll typically be a horizontal line, and later on when we'll look at other polynomial functions, it could be other shapes than lines, but for now, this will tell us what our end behavior for the graph is. So we want to graph these functions, state the domain and the range, and also their end behavior to do our introduction here to graphs of rational functions. So let's look at these two problems. Starting with this one, what I want to do is to get it into the format. We're going to try to get it in the format here where we have this format of a fraction plus a constant. The way to do that is to use our polynomial long division. We could also use synthetic division, but I'm going to do polynomial long division just to review. So for this one, it will be x minus 2 divided into 3x minus 4. X times 3 gives me that 3x. So 3 times x is 3x. 3 times negative 2 is negative 6. I'm going to subtract, and when I subtract, I get a positive 2 from negative 4 minus a negative 6. So my format for this, I'm just going to rewrite it. Y will equal this 3 plus the 2 over this divisor x minus 2. Now notice that this is in the reverse direction of what we had above. What we had above is we had the fraction first and then adding the value. We can leave it like this instead of always switching it back because it means the same thing. But what this tells us is that our vertical asymptote is going to be x equals 2. Our horizontal asymptote is going to be y equals 3. Now what that does is it tells us the domain and range. The domain for this is going to be just that x cannot equal 2. It's every other real number except for that. And on our graph, we're going to see a vertical asymptote right here at 2. All right, and then for our range, what we'll see is that our range is that y cannot equal the 3, okay, related to that asymptote. So I'm going to draw a horizontal asymptote at 3 here. So those are related, the vertical and horizontal asymptotes to the domain and range. Now we also want to state the end behavior, but let's go ahead and graph it first. So I'm gonna give a chart from the table. If you put this on your graphing calculator, come up with some values that will help you get the shape of it related to these asymptotes. What I came up with is -6 goes with 2.75, and I got 0 goes with 2, and I got 1 goes with 1. So let's plot those points here. -6 goes with 2.75, so right about there, getting close to that asymptote. 0 went with 2, so it comes in and it goes through 2, then 1 goes with 1. That shows how it starts arcing down and goes like this, close, very close to those asymptotes, but not actually reaching the asymptotes. Also remember not to let it curve back away from the asymptote. Now, I'm going to put here too that on your calculator you'll see an error, and that's just to emphasize that's x equals 2, not allowed to have 0 in the denominator, so it's our asymptote. Past the error, or past the asymptote, for my table I got 3 goes with 5, I got 4 goes with 4, and then I just went out a little further and went out to 10 and got 3.25. Okay, so if I go 3 goes with, let's see, 3 goes up here with 5, 4 goes with 4, and 10 goes with 3.25, getting closer to this asymptote. Notice that it's going to curve close to the asymptote. You use these points to give the shape of it, and then I get my hyperbola in those two quadrants from the asymptotes. All right, now let's discuss the end behavior. This is what's different about rational functions than what we did with polynomial functions. Those polynomial functions, we typically had our behavior going to infinity or negative infinity. For these, as x goes to negative infinity, the y, notice the y, as we go to negative infinity, the y is just getting close to this asymptote. It's just getting close to my horizontal asymptote of 3. So y is going to 3, where that horizontal asymptote is. As x goes to positive infinity, notice that the y also in this direction, as I come here, it's getting closer and closer to that line at 3. So it also goes to 3. So the end behavior here is related to that horizontal asymptote. All right, let's try another one. Let's do this one number 2 here. I'm going to go ahead and do my polynomial long division for this one. So I'm going to take my x plus 5. I'm going to divide it into the negative 2x minus 6. X goes into negative 2x, negative 2 times, multiply, you get negative 2x, and then I get a negative 10. I'm going to subtract those two. I'm going to get negative 6 plus 10 is going to give me a positive 4. So my fraction, when I write this out then, in the form that I've got it here, it's going to be y equal to the negative 2 plus the 4 over the divisor x plus 5. Now, like I mentioned before, I can leave it this way. I don't have to switch it back like I did before. So now this is going to be this x plus 5. That's going to give me my vertical asymptote. And my vertical asymptote will be at x equals negative 5, the opposite of that, what will give me 0 there. And so my domain that x cannot equal negative 5. It can equal any other value except for negative 5. Now let's go ahead and do the horizontal asymptote. That's related to this number in front. Y will equal negative 2 for my horizontal asymptote. So for this one, remember this is related to my end behavior. So y equals negative 2, so my range is going to be that y does not equal negative 2. It can have a behavior getting close to it, but it doesn't actually get to that negative 2. So let's draw our two asymptotes. X equals negative 5 is over here. And then y equals negative 2 is right here. All right, now for this, I'm going to go ahead and list for us a table that I came up with for this x and y values. Okay, what I started with for this one is I started at negative 9 and I got negative 3. I had negative 7, went with negative 4. Negative 6, went with negative 6. And then at negative 5, notice that we can't equal that. That's where I got the error showing where the asymptote is. So let's plot these. Negative 9, we're at negative 1, 2, 3 down here. Negative 7 is at negative 4, right there. And then negative 6 is at negative 6. So, oops, gotta go a little lower for that one to get down to negative 6. Okay, so negative 6 down to negative 6 down here. And now I'm going to draw my hyperbola graph here where it shows that part of the graph. These points just give the shape of it. We know what the asymptotes do, but this just helps us see where the curve occurs. All right, and then I've got points past this. I've got negative 4 goes with 2. I've got negative 3 gives me 0, and negative 1 gives me negative 1. So negative 4 goes up to 2, and negative 3 goes through 0, and negative 1 goes down to negative 1. And so I've got my graph coming down like this, and curving, getting closer to that asymptote the further out we go. So notice that both as we go to negative infinity and positive infinity, both of these are getting close to this horizontal asymptote at negative 2. Now they don't actually get there, but end behavior is what are you going to? What direction are you going? And they're both squeezing in on this negative 2. So for my end behavior, as x goes to negative infinity, the y is going to that asymptote of negative 2. As x goes to positive infinity, the y is also going to negative 2. So what we start seeing is that the end behavior on these, it's not always going to be that case, but with this linear over a linear, it tends to be that they go to the horizontal asymptotes and go to a single constant value. So we need to look at doing, if we want to get it into this format where we graph it similar to what we've done before with a fraction plus a constant giving us these asymptotes, you have to do the polynomial long division to get that format. Then look at the denominator, that will give you your vertical asymptote. Look at the constant that's outside of it, that will give you your horizontal asymptote. And then the new addition that we added was to look at end behavior. And end behavior here doesn't go to infinity and negative infinity. It instead comes in on these asymptotes when we graph these specific polynomial over polynomial rational functions.